Hey everyone, I'm Sai Madhu and welcome to Data Aspirant YouTube channel where we don't just talk tech, we turn into your superpower. Today we're diving into a game-changing topic that quite powerful, everything from ChatGPT's memories to Spotify movie recommendation. Yeah, we're talking about vector database. Here is a crazy example. Snapchat uses vector database to instantly surface similar filters from your past usage in milliseconds. That's how fast these smart systems are. And guess what? You can build similar capabilities with open source tools available today. If you're already playing with tools like ChromaDB or Pinecone, feel free to skip ahead and go to the deep dive session on applications and inner working of vector database. But if you just heard the term vector database and you're wondering, do I need this in my upcoming project? Stick around. In this video, we'll break down everything about vector database and we're going to build one application using vector database. So it will be hands-on session at the end of the video. So let's get into that. Now you might be thinking, why do we need vector database when traditional databases already exist? Very great question. So picture this, what if your search engine or voice assistants could understand what you meant, not what just you typed. Even you mess up with keywords or say it into your own words, it get it right. Sounds like magic, right? That's exactly where database or like vector database will comes. Ever used a chatbots or that seems to be remember what you already chat with and got a product recommendation that was so on point and it felt like it read your mind. Those moments, that accuracy and that understanding, it's not luck, that comes from vectors doing and heavy lifting behind the scenes, and vector database or the engines that make it feel all work lightning fast and very accurate. All right, now that you have good sense of why vector databases are really important, let me quickly walk you through what's coming up in this video so you know exactly what to expect from this video. First, we will explore the limitations of traditional SQL databases and why they fall short when it comes to tasks like semantic search or AI driven recommendations. That's where the database will come, the vector database will come, and we'll break down how it exactly works. Okay, then we will look into the original story of vector database, how they come and why they are suddenly everywhere in the AI applications. After that, we'll dig deeper into the core mechanics, how vector databases actually work, what vector database and what vectors, what are embeddings, and how they help machines understand beyond the exact words. We'll also check out some of the most popular vector database or vector database platforms, ChromaDB and Pinecone and many more. And we'll talk about what to use and when. That will be really helpful. And of course, we're just not keeping up theoretical for this video. We are going to build a working example from scratch using ChromaDB to show how you can integrate a vector database in your own project. By the end of this video, you won't just know what vector database is, you'll actually be able to implement one in your personal project or even pitch it to a solution in your current role. Before we jump in, if you're finding this video really helpful and you're learning something new, feel free to hit the like button and subscribe if you want to more similar real world AI and Gen AI content like this. Let's say you just watched Inception movie, that mind blending sci-fi movie where dreams within the dreams twist your brain like fragile. Now imagine you go to any movie app, it can be Netflix, it can be Prime Video, and you typed show me like Inception or like intelligent, a bit dark with sci-fi and psychological theme. Here is the problem. A traditional SQL database would search for exact matches, look for genre sci-fi or title contents Inception. That's it. It doesn't understand what intelligent or sci-fi means. No concept of similarity or vibe. It's all rigid filters. But what vector database? That's where the magic will happen. Behind the scenes, your movie plot, your user queries, or even trailer transcripts is converted into a vector, a high dimensional representation of its meaning. Now, using vector similarity or like cosine similarity, the system can retrieve movies with similar concepts, even they have different or completely different keywords. It will find Interstellar, Shutter Island, or Tent, not because they share same genre, but because they feel like Inception. That's the power of vector database. They understand context, meaning, and nuances, not like traditional SQL that don't understand these context. All right, let's bring this home with one more powerful example, because once you see it, you will never look at the traditional database the same way again. Let's break down another real world scenario to show the limitations of traditional database clearly and how vector database completely change the game. Imagine you're shopping online for a socks. So you typed show me Kroji winter socks with minimalistic design, something you would wear at a mountain cabin. Now, here how the traditional database handles the same request. It might look category is equal to socks and color is equal to white, maybe keyword like winter and all. Result, you'll get 500 random socks somewhere with some neon pink and radiant, and one pair that technically glows but misspelled as socks. Why? Because SQL is keyword based. It's not having any idea what quasi or minimalistic actually mean, and certainly no idea what mountain cabin feels like. Let's say the same with vector database. With vector powered search, your entire query is transformed into semantic vectors, capturing the vibe, the intent, and even the emotions behind the words. The system captures your query vectors with product description vector, not just keyword but embedding meanings. You will get a short list of socks that are soft, warm, stubble in design, and maybe even comes from eco-consistent brands, exactly what you had in your mind without spelling it out. That's the power of semantic search, and that's what the vector database are providing. So where did vector database even come from? To understand that, let's rewind a bit. It's all started with vectors, a concept straight out from our high school math. You probably remember them as arrows with magnitude and direction. But in AI world, vectors become much more powerful. They started representing the meaning. Fast forward 2010, when vector embeddings like Word2Vec, Glow explode onto the scene, though these models can turn words into vectors, and suddenly machines could understand language semantically. Like king minus men plus woman is equal to queen. That blow everyone's mind. But here is the problem. Once we had all these high dimensional vectors of words, sentences, and even images, we need a smart way to store them and search through it very efficiently. That's when we need vector databases. At first, people hacked some solutions using Elasticsearch or PostgreSQL with cosine similarity, but it didn't scale well for millions of vectors. These systems weren't designed for highly dimensional search. That's the one of the reason why it is lacking. Then we came specialized players like Facebook released FIS, FAISS in 2017, a super fast vector search library. Spotify dropped Anonym, their own tool and recommendation music using vector similarity. Google started embedding vectors tech inside their own infrastructure. And then came full-fledged vector databases like Pinecone, Weaviate, and Quad, and Milvus, and ChromaDB, built from ground up to do only one thing very efficiently, that is semantic search at scale with high speed. Now, with the rise of generative AI and RAG, retrieval augment generation, and the multimodal applications, vector databases aren't it just useful, they are very fundamental now. So what started as a math concept now has become a backbone for all the intelligent systems, from chatbots that remember context to search engine to get you the results. And we're just getting started. Now that we know what vector databases are and why they matter, let's break down how they actually work in a way that's super simple and fun to understand. Imagine you are going to a music store. There are million songs, and you walk in and say, "Hey, I want something that feels like a song, blending lights by the weekend, but maybe with a chill vibe." Now, a traditional database would search by artist name, genre, or like year it is published. It might give you the weekend's album, but it won't understand the feel or vibe you're talking about. But here, where the vector database change everything. In step by step, let's see how it works. So the first step is embedding. So it's like turning the meaning into numbers. Before anything goes into the vector database, we need to run through a embedding model. Think it the embedding model something like a super smart brain that translates the context, like it can be images, it can be text, it can be audio, into the list of numbers that we generally call as a vector representation. Just to give an example, right? The plot of Inception becomes like a 384 dimension vector. A voice command like play relaxing music becomes another vector. A product description or like legal document or customer review, anything get be like vectorized. Each vector captures meaning, emotion, and context in a way the machines can understand, not just by keywords. So the second step, by now we have like any context or anything, we convert it into numbers that we are calling vectors. So the next step is indexing. So imagine you have the millions of vectors. We cannot search one by one. That will be really painful, right? And it is too slow. So we use something called vector index. Think it of like a super organized library, so you can retrieve much faster. So we have like popular indexing techniques, something called HNSW, hierarchical navigable small world, and we have something called IVF, inverted file index. These are we have others also, but people generally use these two. So using this indexing technique, we can search millions of vectors in milliseconds. So the third part is semantic search. So when you search movie like Inception, right, your query gets converted into vectors, basically converted into numbers. Then the database then captures your vectors, which will store vectors using cosine similarity. The third part is similarity search. When you search movie like Inception, your query get turned into a vector. Then the database then compress your vector with all the sorted vectors, basically which one is much closer, using a vector similarity, a mathematical way to check how close two vectors are in a meaning wise. So vectors that point in similar direction means a similar context. You'll get Interstellar, Tenant, and Shutter Island as a result. Let's connect the same thing with our product recommendation example. In our product recommendation example, when the user type Croji winter socks with minimalistic design, so the sentence converted into vectors, then the vector database compares it with the product description, also stored as a vectors. So and brings back the similar items even if they don't have exact words. So in short, if you want to compress this, right, we have like three things. One is we need to create embeddings for every context or any text. You need to convert it into word embeddings, translating meaningful numbers. The second thing is indexing. This is for faster retrieval. The other one is semantic search, finding contents or like context which are much closer from a similarity or like a semantic wise. So these are three things are important when we're discussing about vector database. So embeddings, indexing, and similarity search. So this is why vector database are revolutionary. They allow missions to search by meaning but not just by exact match. And that's what makes them like secret sauce behind everything from the smart chartboards or like personalized recommendation. If you are finding this video really helpful so far and you're learning something new, feel free to hit that subscribe button and like button. If you want more stuff from the real world AI or like content related to Gen AI, so we have like tons of practical breakdown videos coming on the way. Don't forget to subscribe. Alright, now that you have got solid understanding how vector database work behind the scene, now let's go one level deeper and let's understand how they work actually with from a technical side. So if you really want a smart or like master vector database, whether you are comparing them or like building something new or you're just exploring this space, right, you need to understand the three core concepts we discussed. One is embeddings, the other thing is high dimensional indexing, the third one is the similarity matrix. Don't worry, I will break down in a much simpler way. Let's understand one by one. Okay, let's start with the word embeddings. So imagine you're trying to teach a computer how the cat will look like. We cannot just say like keywords like furry or like memes or like black or color kind of thing, right? We need a representation of the concept of cat in a format that mission can understand. That's where the embeddings comes. An embedding like a digital footprint, a long list of numbers. It varies. The dimension can be varies, but that captures the meaning of something like a sentence or image or like video, audio. For example, a dog is a friendly pet. Maybe that sentence can be converted to a 384 dimensional vector like 0 0.1 minus 0 0.2 minus 0 0.8. Likewise, we have 384 dimensions. These numbers are generated by machine learning models. They're trying to recognize patterns. That's where the magic will come. Items which are similar, right? If the two texts are similar semantically, they might come together or like too closer when we check cosine similarity kind of thing with the vectors. Now comes the semantic search. How we're comparing these two, right? That's where the distinct matrix comes. These are mathematical ways or like mathematical formulas you can use. This will result if you give two vectors, it will compute and say whether these two are closer or not. That's what it will do. So we have something called Euclidean distance. It's like drawing a straight line between 2 points, and the smaller the distance, they are much closer. And we have something called Manhattan distance. It's a similar thing. If the smaller score, you will get more similar. So the popular thing is cosine similarity. It basically measures the angle between the two vectors. If they point the same direction, they are much similar. Just to give an example, right? A image of cat and tiger have high cosine similarity, because both are a bit of similar. But a cat and car will have so much of difference. That's what this cosine similarity will give us as a matrix. So different models are trained with different distance metrics. That's why make sure when you're using any embedding model, try to understand what distance metrics they're using. So the other one is high dimensional indexing. So now we have this vector and all. So there has to be smart way to retrieve, right? That's where the indexing will comes. So vectors, we when we embed the vectors, we have hundred or thousands of dimensions. Cannot visualize that, but imagine you're trying to find a closest point in the space, right? It will be pointless. It will be so far. That's in a machine learning times. If you have more dimension, we call it as curse of dimensionality. Now, if you tried search every vector manually, that will be a brute force approach. It will take forever, millions or like billions compared to the request you're having. Not practical actually. So we use some concept called ANN. It's called approximate nearest neighbor indexing. We have so many techniques to perform the same. Maybe I will give a high level overview for some of them. The first one is IVF, inverted file index. It groups vectors into clusters using something called k-means algorithm. That's a machine learning algorithm. When you search, it checks only the most relevant clusters, not the whole database. So that's why it will be fast, efficient, and also widely used. The second one is HNSW, hierarchical navigable small word. This builds like a graph of vectors where each one is linked to the other one. It will start from the high level and also go to the levels where the data was there or like where the similarity is matching. It's a default for Weaviate or like Milvus. Third one is like tree-based methods. Tree divides the spaces into zones. It's only search for the zone which we need to refer. From a memory wise, like a great memory efficient, we can observe from the tree based methods. So the other one is LSH, locality sensitive hashing. So it uses hashing functions. So similar vectors will be labeled into same buckets using the vectors. It is super fast, but it will work only for the low data, low dimensional data. For higher dimension, it's not a better option to pick it up. Putting it all together, these indexing methods help vector databases avoid brute force scanning, deliver lightning fast results, handle millions and or billions of vectors efficiently. And here is the cool part. Most databases lets you tweak these indexes or like settings to balance speed, accuracy based on your needs. So now you understand how vector database works, you might be wondering which one I should actually use. Very great question. Because there is no one size fits all. Just like choosing a car depends upon whether you're racing, off-roading, or going for trip with family. Picking the right database depends on your usage, your scale, and your goal. Let's look at the top players in vector database space and we will learn which one you need to use when. Let's start with Pinecone. Pinecone is the Tesla of your vector database. If you want performance, speed, and don't want to manage anything yourself, Pinecone is your guy. It's fully managed, lightning fast, and built for production scale applications like real time recommendation engines, personalized search, or LLM memory system. It helps in the scenarios where you need advanced metadata filtering, want automatic scaling, handle millions of queries per day. This is the ideal one. But a fair warning is it's not cheap and not as customizable as the open source tools. Ideal for teams with budget and scale in mind. The second one is ChromaDB. This is the open source favorite for LLM builders. If you're experimenting with LangChain, Llama Index, or building your first RAG pipeline, ChromaDB is the perfect. Why? It's lightning fast, simple to set up, and works beautifully with Python-based AI tools. It's like your Jupyter notebooks of vector database. Great for learning, prototyping, and iterate fast and don't push it too much for massive scale. Why? Because it's not built for that. The third one is Weaviate, the modern all-rounder, you can say. Think Weaviate as a as an army knife of vector database. It's open source, cloud ready, supports GraphQL and REST APIs, and even lets you combine structured plus and unstructured data also. It's a go tool if you're building for semantic search or knowledge graphs, or you need something flexible that plays well with various media type like text, image, or even audio also. Plus, its modular architecture is dream for very so many developers. Fourth one is Milvus. It's the heavyweight champion basically. If you're building something massive like a search engine or like billions of documents you need to process, Milvus is the ideal choice and it built for that war. It's optimized with GPU accelerators and supports multiple indexing methods we discussed, right? Like IVF, HNSW, and PQ, and gives you the full control over the performance. Use Milvus when speed and scalability are massive critical for your project. But B1, it's more complex and the learning curve can be steep for beginners. That's what I would suggest. The last one is Qdrant. This is the developer sweet spot. Written in Rust, yes, it's fast and efficient because of that. Quad offers a great balance between performance, flexibility, and ease of use. It supports advanced hybrid search, payload filtering, and real-time updates. Perfect for modern recommendation systems, semantic products, or personalized engines. If you want something open source, powered with too much of complexity, Quadrant might be your best bet, I would say. So let's quickly recap. I have list down use case wise what are the best choice. I will pause the video for a second. Please take a screenshot and take this as a reference whenever you want to build something, right? Just use this reference to select what vector database you want to build. So the next time you are building a chatbot, a semantic search engine, or recommendation system, remember your choice of vector database could be the secret ingredient that makes your app magical. Upon next, let's take this learnings or this understanding to the next level. Let's build a project purely using ChromaDB. Ready to get your hands dirty with the coding? Let's get there. And if you find this video helpful so far, go ahead and hit that subscribe button and share with your friends and teammates who are exploring AI or Gen AI or building some cool features they want to thinking to build, right? Also, if you haven't already, click that subscribe button and help us creating this kind of content every week. Now I got a question for you guys. So if you're curious to see full and tutorials like this, any of the vector database you're interested, or you want to see head-to-head comparison between two popular vector database, just drop a comment in the comment section. We're always listening, and based on most requested or like most upvoted comments, we'll create a detailed in-depth video or blog post which will explain everything you need to learn. All right, we covered the theory. Let's explore the tools and let's see how we can build our own vector database and use that vector database in any of your project. For this demo, imagine we are building something called semantic document search. User will type a plain English query and our system will return most relevant pieces of text from the documents collection we have. So it's not like actual keyword based, it's more like a semantic meaning documents also we need to pull it up. So think of it as like a mini Google search but focusing on understanding meaning of the word, not exact keyword. Okay, let's say if someone searched feline pet, the system should able to return the images of cat even though we haven't explicitly said cat we want, right? That's what we are gonna build. So if you want to, basically the steps we will be following is at the first step we will prepare the data set, and in the second step we will generate embeddings using a pre-trained model. Then we'll store that embeddings to the ChromaDB, and we will request user to get a query and we'll convert that to embedding, and we'll see what is the closest match for this query and return those documents. That's what we will be doing. By the end of this hands-on project, you will see exactly how embeddings, similarity will work and vector indexing work, right? Everything will combine. We will learn together by implementing this use case. This is something you can expand to your chatbots or like your custom systems, or even plug into your GenAI workflow, which is working under the hood of RAG. Okay, let's jump into the coding part now. So let's see how can we build the semantic search we discussed, right? So I'm sharing my editor code editor here. So I'll keep all data sprint scripts here. So let's create a new folder here. Okay. So I'm naming it as semantic SEO semantic search. Okay. So inside that, let's create a file. So new file semantic search.py. So let's click enter. So let's say first we'll import the packages. Just to save some time, I'm just pasting the things I already implemented. So we are imported a sentence transformer, and we will see why we are importing sentence transformer here. And then we imported ChromaDB. From ChromaDB utils, we imported embedding functions. Okay, these are the things we needed. Then so first what we need some list of documents which we will be using. For on top of that, if user is asking question, we need to use the semantic search to identify the semantically matching documents. Okay, for that we need documents, right? Let's have the documents here. So these are the sample we have. So if you see, we have like 1 2 3 4 5 different documents we have given. Also as a description I given what this document is actually talking about. Okay, just for a reference I'm giving this. So now that we have documents, what we will do is, first of all we will load a embedding model. So I'm just copying the script. So if you see whatever we are doing, we created instance, right? Sentence transformer, and this is the model we are using from Hugging Face basically. Okay, this is the popular lightweight model with 384 dimensions embeddings it will create. Okay, any text we are giving, it will convert into 384 dimensions of embedding vector. Okay, so just we created a model. Now what we will do is, so we need to compute the embeddings. Okay, so here is the script for that. What we are doing, we are basically calling the model dot encode documents. Documents is nothing but these list of documents. Okay, so we're doing this, and this will return a embedding vectors one. Okay, I want to see how it looks, that's why I given this one. Okay, I'll execute and show you how it looks, but just for simplicity, once we have the embedding, let's go to the next steps. Okay, we'll execute the entire script once. Okay, now I'm just initializing the client for ChromaDB. So this is the way to do that. We have ChromaDB initiated, and on top of that we are calling the method client. This will define, which basically initialize the client for us. Now, so let's create collections vector. So let me, so this is the approach. So once we have a client, we will create collection. Basically we are giving the name for our vector database that we are calling as doc search here. Okay, this is the name. It is important. Why? Because next we are referring, right? You need to refer with the this name. It's basically doc search for in this case. Okay, now we already created the collection with the name of doc search here. Next, what I'm doing, I'm just so for that collection, what are the embeddings we created here, right? Doc embedding that we're adding. So we'll have a document, and also we have doc embeddings that we computed. This is the doc embeddings, and we are appending that. Okay. With this, what happens in the collections? We added all the embeddings we generated. Once we printed this, we'll get that information. We'll see how it looks like. Okay, once we run the script. Now we have documents, we have embeddings also. Now let's get some user query. Okay, so will copy the entire thing. So next, what we are doing, we have a user query. It's like domestic animal. What we need to do now, once we have the user query, we need to convert it into embeddings, and we need to see this embedding is matching with what documents embeddings we have. The closer the thing, that we will generate as output. Okay, that's what we are doing. We're converting here to embedding again using the model we defined, that is a sentence transformer. So once we have that, then we are performing the similarity search with this functionality. So what we are doing, we're querying with query embedding that we generated here, and we are saying like I want three results. Once you search, right, I want the top three results. And what we included is I want document, and what was the distance matrix, how close it is in the vector database dimensions wise, how close these two user query and the results we got, right, how close these are. That's the value we're getting. Okay, and then we are printing that here. Okay, so I hope this is clear. I'll quickly give a walkthrough again. So we initialize the required packages here, and we have some sample documents. In this case it is text. Then we define the model. It is called a sentence transformer, all mini. This is the lightweight model. And what we're doing, what are the documents we have, we converted everything to word embeddings. Then we initialize ChromaDB, and we given a name to ChromaDB, that is doc search. And then we iterated everything and created embeddings, already created embeddings and documents. We stored it in the collections. Okay, then we have a query for the user. We converted that to a embedded vector, and then with similarity we're trying to get the top three results. Okay, while printing, I want to see what are the documents we identify closer, and also how much the distance we are representing. That's what I want to print. That I'm doing here. Okay, now we have everything. Now let's compute this and see. Okay, so now what I will do, I will activate the environment we have done previously. Okay, now I will go to 3D documents. So documents, environments, let me see what the name I have given, semantic search, right? So I will say source semantic search bin activate. So this will activate our environment. Now the environment is activated. I'll just see. Okay, this is the environment. Okay, now what I will do, I'll go to the directory where I'm storing the codes. Okay, where we are storing that inside the data aspirants codes. Okay, so it was in documents actually, cd. So I'll go backward, documents. Okay, now cd projects, data aspirant codes, and then semantic search. Okay, so ls cd. Okay, fine. So it basically the PCA code I haven't pushed to Git. That's why it is showing that, but don't worry about that. For this video, it's not relevant actually. So now I'll see semantic search. Okay, now let's execute that. What should we expect? So we are printing three times, right? This is the embeddings we're printing, and also once we dump that we're printing, and the final results basically. So the top three results for this query, domestic animal, and what were the distance. This is what we can expect. Okay, so let me now Python and semantic search. Okay, let's run this one. Let's see what it comes up. So semantic search, why it is not printing? Okay, I think I haven't saved the file. Okay, so let me run again. So it is taking time to compute and all. Okay, yeah, see, these are the 5 documents we stored. Okay, and those two are completed. It is giving the dimensions here, and how many collections we added to the vector search, not vector search, what is the name we have given? Doc search. How many records we have stored, that we are getting here. Now for our query, what was the much closer domestic animal we said, right? Even though we haven't mentioned cat and dog, right? If you see the results, we are getting dog, cat and kitten, basically the cat. Okay, and also we got what were the distances we are getting. Okay, so I think it's working. Let me try for one more thing. I will say what you guys want me to try out. Let me think and let me add. Okay, I will change it to sweet. F for is sweet fruit and pastry. Okay, this is what I'll try, and let's see how the results are coming. Okay, let me go back. Let me run this Python semantic search. Okay, let's see the results. It is taking time to compute. Okay, I think these two will be common anyhow. So if you see, we talked about fruit, right? Instead of cat and dog, we got apple. Even though we have mentioned uh, what we called we haven't called the apple. It is coming because it is 0.08, okay, distance, and a dog is a domestic of family candidate. I think a cat is a small domestic animal. I think in the documents, I think this was the wrong answer. Okay, why it is wrong? Because in the documents for fruit, we have only apple, I guess. That's why we are getting this, which is much closer. But what we said, I want three results, right? That's why the next two results also coming. But if you define thresholds properly, or like you define only one result or two results, right, then you can eliminate this. But here, this is not an expected answer. Okay, because in the documents we don't have anything talking about fruit, that was not coming. But ideally this is the response, it is coming. Okay, at this point, you have built a working semantic search engine. So let's recap what we have just built, right? We took set of documents, we converted them into vectors, and using the pre-trained model I have shown. Then we stored those vectors in ChromaDB, which automatically handles the indexing. Then once user types a question, right, we converted that to embedding. Then we'll compare which one is much closer to the documents we have. That's what we're resulting. Okay, this is the core functionality of semantic search, and this is the exact techniques how we need to implement. So using this, you can build AI powered search engines, chatbots, or like RAG based LLM apps also you can integrate. Okay, I hope this learning will helpful for you to build different applications using ChromaDB as a vector database. Let's take a quick step back and recap what we have just learned. So we started with why, understanding what makes vector database different from traditional databases. Instead of matching just a keywords, right, we know now using the vector database you can find the real meaning. That's the massive leap forward for the modern applications we are intended to build. We learned about embeddings, distance metrics, and different indexing techniques like HNSW or like IVF, and we also learn how these techniques will make or like search millions of vectors with much faster. In milliseconds you're getting results, right? So we also explored the real world tools, or like we compared different vector databases and we identified which one we need to pick, right? Also just remember the screenshot we have given, right? Try to keep it that and also use that reference whenever you're building something new. Then we make our hands dirty and we build our own semantic search engine. I do agree we are just using a text, but the idea is using that you can build for any documents or images or anything. It's just a matter of converting the data to a embedding. So, and that we build using ChromaDB. With this, what was the next you have to do? Okay, with whatever you learn, try to integrate that with your semantic search apps, or like build your own recommendation engines, or even give AI assistants the memory that understand context, not just the keyword. If you found this video helpful, give it a like or drop the how you feel about the video in the comment section, and don't forget to subscribe our channel for more hands-on generative AI and data engineering concepts every single week. Now go out there, build something amazing with vector database, because the future isn't about just storing data. It's more about understanding the data, like the humans do. Thanks for watching, and always happy coding. And a quick sneak peek of the next week's video. We're diving into something super exciting, which called vibe coding, and we will be building an amazing application end to end using Replit. Okay, plus I will also show how we have to deploy that application and how to add the auto scaling functionality. Let's say more users are accessing your application, right? How you need to auto scale the application, that we will be discussing. So if you are into the next gen, if you are more interested in the next gen like AI applications, don't miss the next week video and hit that subscribe button and make sure you are here in the next week's drop. Thank you.